Hello everyone, welcome back to Neural Network Lectures. In the previous lecture, we have learned about Hebbian learning and also I introduced you to competitive learning, right? In this lecture, we will be continuing the discussion on competitive learning and also we will learn about Boltzmann learning. Okay, so those who haven't seen the intro on competitive learning in the previous video, I strongly recommend you to watch that before coming here so that it will be easy for you to grasp the ideas being discussed here. Okay, having said that, let's start our lecture. In competitive learning, as the name implies, the output neurons compete among themselves to be active. That is, at any point of time, only one of these output neurons will be active. Okay, this is in contrast to the case of Hebbian learning, where multiple output neurons may be active at the same time. So, this is a very distinguishing feature of competitive learning. Always remember that. Okay, I have discussed about this in a detailed manner in the last lecture. So, if you have any doubts, please refer that. Okay. Now, let's move on to the basic elements of competitive learning. There are mainly three basic elements to competitive learning. The first one is a set of neurons that are all the same except for some randomly distributed synaptic weights. What it means is that all the input neurons are structurally similar. The only difference among them is that the synaptic weights at the beginning or initial synaptic weights of these neurons will be different. They will be randomly distributed. Okay. Now, the second point is a limit is imposed on the strength of each neuron. What it means is that some constraint is put on the synaptic weights of each neuron. For example, it can be like this: sigma wkj iterated over j is equal to 1 for all k. Or it can be like this also, that is sigma wkj square equal to 1 for all k. These constraints put on the synaptic weights depend upon the environment as well as the design of the neural network. Okay. Now, coming to the third point, neurons compete for the right to respond to a given subset of inputs such that only one output neuron is active. It simply means that only one of the output neurons will be active at a time. And for being the neuron to be active, the neurons compete among themselves. Okay. So these are the three simple criteria on competitive learning. Okay. Now we will talk about the network architecture of competitive learning. In competitive learning, all the input neurons are connected to all the output neurons. Also, there are connections between the output neurons. One important thing to note is that all the connections between the inputs and the outputs, that is, these connections are excitatory in nature, while the connections between the output neurons, that is, these connections are inhibitory in nature. Why? Because the output neurons are competing among themselves, right? For that, each output neuron should try to suppress the output of other neurons. That's the reason why these connections between the output neurons are inhibitory in nature. And these connections are called lateral connections. Okay. Now, how will we choose the winning neuron? The condition for a neuron K to be the winning neuron is that its induced local field Vk, where this Vk is equal to sigma xj wkj. I hope that you remember this. Okay. Its induced local field Vk for a specified input pattern x must be largest among all the neurons in the network. Also, the output of a winning neuron is set to 1 and the output of all other neurons is set to 0. Mathematically, we can write it as yk equal to 1 when vk is greater than vj for all j for j not equal to k, and yk will be 0 in all other cases. Okay. Now, suppose that k is a winning neuron, that is yk equal to 1. All the synaptic weights connected to neuron k will be updated, limited to some constraints, like I have told you before, that there is sigma wkj equal to 1 or sigma wkj square equal to 1, etc. Okay. However, the important thing to note is that the synaptic weights connected to other neurons, that is, the loser neurons or the neurons that didn't win the competition, are not updated. Okay, let me emphasize that. That is, the synaptic weights of other output neurons are not updated. Okay, this is how the neural network learns. And the change in the synaptic weights delta wkj for the winning neuron is given by eta into xj minus WKJ if neuron K wins the competition. Okay. In all other cases, it is 0. That is when neuron K loses the competition. Where this eta is the learning parameter as always. And this rule for updation of synaptic weights is called competitive learning rule. Okay. This rule has an overall effect of moving the synaptic weight vector Wk of the winning neuron K towards the input pattern X. What I meant is, suppose we have an input vector X which is given by X1, X2, X3, etc. to Xn, and we have a synaptic weight vector Wk given by Wk1, Wk2, etc. to Wk. Okay. Over the time, as the learning progresses, this weight vector Wk will approach the input vector X. Okay. That is how the output neurons become feature dictators. From this point that the synaptic weight vector will approach the input vector, we can infer that the input vector is also under some constraints. For example, let's say that the weight vector Wkj is under constraint that the summation is 1, then there's a possibility that the input vector is also under the same constraint. Okay. To make this point more clear, let me take a two-dimensional vector, that is x equal to x1 and x2, and wk equal to wk1 and wk2. Okay. Now let the synaptic weights be under the constraint sigma wkj equal to 1. Okay. So the synaptic weight vector will move around a unit circle in a 2D plane, right? Therefore, let me draw that. Now, let these dots represent the natural grouping of input patterns. Okay. And let the initial state of the synaptic weight vector be like this. Okay. Let this process represent the synaptic weight vectors before the training. Now, as the training progresses, the synaptic weight vectors will move towards its natural groupings like this. So the final state of this process will be over here, this over will be here, and this will be over here. So it can be said that each output neuron has discovered a cluster of input patterns by moving its synaptic weight vector to the center of gravity of discovered cluster. Okay. Now if we try to implement this on a 3D plane, let the clustering of inputs be like this, and like this. And the initial state of the synaptic vector may be like this, or like this. And over the time, due to learning, these synaptic weight vectors will approach a clustering of inputs. Okay. So the final state after learning will be the synaptic weight vectors will be at the center of these groupings of inputs. Thus, for example, this particular output neuron has specialized in detecting this group of inputs. Okay. Similarly, this one has specialized in detecting this group of inputs, and this one on detecting this kind of inputs. Now consider the case that there is two groupings, okay, that are very close to each other and overlap. Now suppose that a synaptic weight vector has approached this clustering. Okay, let this be over here. However, due to this overlapping of inputs, the synaptic weight vector won't be stable. It will begin to oscillate between these two clusterings, that is these two input clusterings, making the system unstable. This is a shortcoming of competitive learning. Okay, so keep that in mind. Now let me try to show you how a neural network learns to play a game. Let's take the classic example of Mario. So the input vector to the Mario may be the pixels in front of Mario. For example, let the input vectors be the pixels here. Okay. And Mario has only three outputs. That is moving forward, moving backward, and jumping up. I hope that you all remember the moves in Mario. That is, it can only move forward or backward or jump up, right? Therefore, 3 output neurons are given for each of the functions. Now, the neural network may not be provided with the rules of Mario. However, for each game played, the neural network will be provided with a score based on its performance. Okay, so the game starts with random weights, and in the initial few games, the neural network may not even move the Mario. The Mario will simply stand there. But all the time, the neural network will learn that its performance score will increase if the Mario moves forward. Okay, so the synaptic weights will be adjusted in such a way that if there is an input vector consisting of this kind of pixels, that is, there are no obstacles, right? There is in this set of input pixels, there is no obstacles in front of Mario. So the neural network will move Mario forward. By the way, keep in mind that as Mario moves forward, its input vectors keep on changing. For example, in this place, these are the input pixels, and these are the input pixels over here, and this is the input pixel over here. This is the input pixel over here. Note that as Mario reaches over here, the input pixel or the input vector will show an obstacle, right? Initially, the neural network may not know that it should jump over the obstacle or jump over the mushroom. However, with many training iterations, it will learn that if the Mario jumps over the mushroom, the performance score of the neural network will increase. So, the neural network will learn that if this particular set of input pattern comes, it should jump. Okay. Similarly, there might come an instant when the Mario should move backward. Likewise, over many generations of training, or the number of times the neural network will play to learn the game will be in the order of 10,000s or in millions. Okay, and eventually it will learn what to do when it confronts a particular input pattern. Okay, this is how it will learn, and thus finally the neural network will learn to win the game. Okay, this is a very crude example, and I hope that you all understood this. If not, there are many videos in YouTube which shows how neural networks learn to play a game. Please try to watch that so that you can learn how competitive learning is applied in real world. Okay. Now, having said that, let's move on to the next learning rule, that is Boltzmann learning. Boltzmann learning rule is a stochastic learning algorithm derived from statistical mechanics. Let me write that down first. Now, it is stochastic in the sense that it is non-deterministic. Okay. Now, the second point to note is that the neurons in Boltzmann learning constitute a recurring structure. What I meant by this statement is that there are feedbacks between the interconnected neurons. Okay. Now, the third one to note is that the neurons in Boltzmann learning network operate in binary mode. That means they take either +1 or -1 states. Okay. Now we can characterize the Boltzmann learning machine by an energy function given by E is equal to, this is by definition, okay, minus half into sigma wkj xj xk, and is iterated over k and j. Okay, and I hope that you all remember the definition, that is xj is the input to the neuron j, xk is the input to the neuron k, and wkj is the synaptic weight from neuron j to k. Okay, and also this equation is restricted to the constraint that j not equal to k. What it means is that there are no self feedbacks. Okay, now the question arises, in what way the Boltzmann learning is stochastic. For example, let's take a Boltzmann network. These are the output neurons, okay, and all these neurons are interconnected like this, like this. Okay, now we can take the outputs from any of these neurons. Okay, or rather we can say that the output pattern is defined as a vector of states of these neurons. Okay, but in a more generalized Boltzmann learning network, there may be some other neurons also in the network, and these neurons doesn't take part in the process of output. However, these may be interconnected with other neurons. Okay, like this, etc. Since these neurons doesn't take part in the output process, we can say that it's a hidden layer, right? In the sense that we don't specify their states in the output. But all these neurons take part in the output process. Okay. So basically we can divide the neuron set into two. That is the ones that take parts in the output and the ones that doesn't take part in the output. The ones that take part in the output, let me mark them, are these, right? These ones. Okay. We can call these neurons as visible neurons. And the ones that doesn't take part in the output, that is these ones, can be called as hidden neurons. So what basically the Boltzmann learning rule says is that the energy function for a particular state of network is given by this equation. Okay, so this is an important equation. Now suppose that some of these neurons are +1, that is the state of these neurons. Okay, like this. Okay, now suppose I take this one particular neuron and flips its output state. That is, I change its output state to +1. What it means? It means that the energy state of the network changes. That is, this energy function changes. Now, what it means in the stochastic sense is that what is the probability that the state of the picked up neuron will be flipped? Okay, you understood that? That is, we find the probability P that a neuron K changes its state from xk to -xk, and this is given by the expression 1 by 1 plus exponential of delta Ek by T, where this delta Ek is the change in energy function as the neuron flipped from plus xk to minus xk. And T is the pseudo temperature. It basically represents the noise in the system. Okay. So in Boltzmann learning, what the network tries to achieve is that over the time, the network will reach a thermal equilibrium. That is, the network will reach a steady state. Okay. Now, another thing about Boltzmann learning is that we have already classified the output neurons into visible and hidden neurons, right? Now, a question that might arise is that are we able to change or flip the output states of all visible neurons? Perhaps we can, perhaps we cannot. The case where we can't change the or we can't flip the output state is when we put some constraint on the states of visible neurons. That is, if we clamp them. Okay. Based on that, we can again classify the visible neurons into two categories. That is, clamped and free running. So, in the case of clamped, the output neurons are clamped into specific states determined by the environment. While in the case of free running, all the neurons are allowed to operate freely. Okay. Now, when it comes to the case of hidden neurons, the question of clamping doesn't exist. Why? Because the hidden neurons doesn't take part in the outputs, right? Therefore, this is always in free running conditions. Okay. Now, we need to specify how the weights are updated in Boltzmann learning. Before going on to that, I need all of you to get familiarized with these notations. That is, rho kj plus denotes the correlation between the states of neurons j and k with the neurons in its clamped condition. And rho kj minus denotes the correlation between the states of neuron j and k with the network in its free running conditions. Okay. And this rho kj plus and rho kj minus can take values of +1 and -1. Okay, depending on the correlation. Now, according to Boltzmann learning rule, delta Wkj is defined as eta into rho kj plus minus rho kj minus. Okay, where eta is the learning parameter. Okay, And this equation is called Boltzmann learning rule. Okay, since it is an introductory course, I'm not going much into the details of Boltzmann learning. Okay, now in the next lecture, we will be discussing about how to implement logic gates using Macaulay-Pitts model and Hebbian learning mechanism. Okay, so if you understood this lecture, please like the video and also please subscribe the channel. If you have any doubts, please do ask in the comment section. Okay, thanks for watching and have a nice day.